Okay, yeah. Well, thank you so much for having me. It's really a great honor to be invited to speak at this event. Oh, I don't need to see myself. So what I wanted to talk about today, sorry, is this sort of very broad picture question of whether a warmer climate means a drier land surface sort of globally. And it's obviously a very important issue, and I wanted to highlight hopefully how our views on this issue as a community have changed over the years, and importantly, thanks to Chris's very pivotal work on this topic. And this whole question is illustrated by this picture that you find a lot on the internet when you Google, global warming. So I need to, yeah, there you go. So yeah, I would say that it's probably fair to argue that in the years 2000s, like early 2010s, most studies were projecting an increase in drought and aridity conditions over land under climate warming, as illustrated by these two studies in Nature Climate Change that I pulled out. One showing, for instance, or studying changes in the Palmer Drought Severity Index, like this index that measured drought conditions, and you can see widespread red patterns on land, meaning things get drier. And similarly on the right, paper arguing for increased expansion of drylands under climate warming, drylands being these water limited regions you can see in red in this little map. And what all these studies sort of had in common, I think, were that they were based on comparing changes in precipitation and changes in potential of evapotranspiration and sort of supply and demand framework, where precipitation is the supply of water from the land to the atmosphere, and PET is the water demand from the atmosphere exerted on the land. And here, I think in this event, we're all familiar with what PET is. But usually when I present this kind of stuff, I always have to remind the audience or introduce the audience to what PET is. It's this sort of elusive quantity that is calculated, and it represents how much water would be evaporated by the surface, by the atmosphere. So if the surface was in that case fully saturated, or maybe just it was free water, depending on how exactly you calculate it. And it depends on the atmospheric temperature, humidity, wind, radiation, and also some surface parameters that we'll see are important. And so it's kind of a let's say weird quantity, but it's nevertheless very important in all these projections, because what happens in these studies is that over land with warming, precipitation increases a little bit, but PET, as calculated from climate model outputs here in this study, for instance, after a CO2 doubling, PET increases more and more homogeneously over land. So that the ratio of the two, which is this aridity index metric that people have been using, actually decreases, meaning that things get more arid, as you can see by these plots and the maps on the lower right, where everything gets redder, so more arid, basically. So yeah, so it's like really this differential changes between precipitation and PET, and this very important increase in PET that's pushing everything into drought, even when actually precipitation is increasing. And nevertheless, around the same time, people started realizing that this is a little bit at odds with what climate models are projecting themselves, because you can look at changes in land hydrology and climate models now, as previous presenters have shown. Chris has done, for instance, in the 2005 paper in Nature, I think. So if you look at what they simulate, you see that they simulate an increase in evapotranspiration, for instance, an increase in globally. These are IPCC plot, an increase in from AR5, an increase in vegetation on the upper right in blue, and you can see that globally all these quantity increases, you can see on the lower right, and that the ratio of runoff to precipitation is not decreasing as you might expect. It's actually fairly steady over time, as you can see in the curve in red. So there's a little bit, I would say, of a apparent inconsistency at the time, at least there was, between those drought and aridity atmosphere-based metrics like the Palmer Drought Index or the P over PET metric. And I would add here actually also projections like driven by climate model outputs, including PET projections made by global hydrological models. So inconsistency between those and many aspects of climate model projections themselves in terms of eco-hydrological quantities. So a little bit of this, I would say, Mexican standoff between the two, illustrated by this schematic here with, blue for more moderate changes and red for more arid changes, basically. And it's in that context that Chris published in 2016 this very influential paper in Nature Climate Change that sort of really, I think, unraveled that knot a little bit. And basically, the idea was to show that we can't really test future projections of PET made by climate models against future observations, right? But in the context of climate models themselves, we can actually, the very elegant idea, I would say, here was to say that in places and in times in the climate model themselves where ET is not limited by water, where the soil is saturated, for instance, we should see that ET simulated by the climate model with its own land atmosphere rules should be equal to this PET value calculated based on atmospheric values, atmospheric variables. And what Chris found, illustrated by this graph here, I'm only showing results for GFDL models, but this was for all Sim 5 models in the figure 1 of that paper, was that if you look at this non-water stressed ET and this increase in the future climate in the pale gray bar here, it's completely overestimated by the calculations one can make with those conventional calculations for PET, right? So again, the way we have been computing PET in these future projections leads to large overestimates of this PET quantity. And in fact, what Chris further showed in that paper was that, as had been suggested by others, but Chris really showed it neatly in that study, was that we had been neglecting in those future calculations of PET changes in some surface parameters that are very important in that equations, include changes in stomatal conductance. As CO2 increases in the atmosphere, plants need to open their stomatas a little bit less, and so they lose less water, even as climate changes. And so that had been neglected in those calculations. As you can see here on the lower left, within the GFDL model, you can see that future stomatal conductance is lower than present-day climate stomatal conductance. So what Chris further showed and further found was that within climate models, if you account for these changes in stomatal conductance, they're such that surface net radiation ends up being the best and I would say the most simple predictor of future changes in ET. If you go back to this figure 1 here, you can see that actually the best predictor of the pale gray bar here is the dark bar, which is this energy only based on surface net radiation or fraction of net radiation that best approximates changes in non-water stressed ET. And I think that was kind of a very surprising result to a lot of people, and I'm not sure we still fully understand why at this sort of large scale that models simulate thing, this is the case. But nevertheless, I think it was a very powerful result. So if I go back to this picture here, one very huge implication of this study was that all these sort of left-hand side studies based on PET and offline calculations were not really, should be regarded with a lot of caution, and were not really reliable to make future projections. And that in fact, because most of these had been made with overestimates of future PET, land drying may be less in the future than previously projected by such studies. So that was a hugely, I would say, influential study that sort of steered the field in a different direction, including, well, maybe we should spend more time focusing on climate model projections of land surface quantities themselves, and spurred a whole suite of research questions. And just listing a few here, for instance, people have found that yes, even at the ecosystem scale measured by eddy covariance towers, for instance, we find that indeed net radiation is a better predictor than those complex calculations for PET. Others have sought to include changes in stomatal conductance in PET calculations. Others have tried to find what other factors contribute to the gap between impact metrics and climate simulations themselves. And a lot of work has been also done trying to understand better what processes are at play in climate model simulations of the land surface to better understand those changes in ecology and hydrology. So yeah, I'll stop here. I hope I'm in time. And thank you so much.
Hey, Alexis, I'm really glad you highlighted some of these points that, you know, I guess Bob Hirsch was saying, now I'm getting confused, but you know, some of these results that have come out over the years, just not everybody gets it. So the more we kind of hammer it home is the better. The other thing I like really is, you know, you say, you know, not really sure why, you know, this energy only kind of approach works. And I think that's a great question. You know, I like this question of why. You know, what comes to mind is the equilibrium evaporation concept, and Priestley and Taylor and Slattery and McElroy and all that. And I think it's got something to do with that, the feedbacks between the atmosphere and whatever the land decides to do. But anyway, yeah, thanks a whole, our cat just fell down. She's struggling. The paper that you let me in on, I really appreciated being a part of that. And this is sort of characteristic of some of my more recent years. I've been generously afforded the opportunity to ride the coattails of some really bright people, and I appreciate that. Thank you.
Thank you.